All right, today we are going to pull back the curtain on one of the most powerful forces shaping our world, machine learning. And to do that, we're going to need a map. So think of this as your explorer's guide to a brand new, fascinating continent. So, where do we even begin?
Well, it actually starts with something you probably do every single day. Have you ever pulled out your phone, started typing a message, and it knows the next word you're about to type? It feels like magic, right? But it's not.
Or how about this one, the unsung hero of all of our digital lives, the spam filter? I mean, think about it. Hundreds of emails can hit your inbox, but it just silently separates the important stuff from all that junk. So how in the world does it know the difference between a note from your boss and some new amazing offer?
Now here's the really crucial point. It's not like some developer sat down and wrote a giant, never-ending list of every single possible spam word or phrase. Can you imagine? That would be absolutely impossible to keep up with.
No, instead of being given rigid instructions, the machine was given examples. It was shown what spam looks like and what isn't spam, and from all that, it was taught to learn the difference all on its own. And that fundamental shift, that's the heart of machine learning.
So to really get why this is such a game changer, we have to look at what came before. Let's call it the old way, and you'll see pretty quickly why it just breaks.
Okay, so on one side, you've got the traditional approach, right? A programmer has to sit there and manually create this huge block list of words. If they see the phrase "for you" in spam, they have to add it to the list themselves. But with machine learning, the program just looks at thousands of emails that you've already marked as spam and figures out on its own, hey, this phrase "for you" seems pretty suspicious. The machine is doing all the detective work for you.
And this gets right to the core problem. The old way is just so brittle. The second a spammer gets clever and changes "for you" to, say, "for you," well, your hand-coded rule is now useless. It breaks. You are stuck in this never-ending, frustrating game of catch-up. A learning system, on the other hand, it just sees that "for you" is popping up in a lot of spammy emails, and it adapts. No human intervention needed.
And this is what brings us to the new paradigm. See, machine learning isn't just a slightly better technique. It is a fundamentally different way of thinking about and solving problems.
And you know, this idea has actually been around for a long time. We can go all the way back to 1959, when the AI pioneer Arthur Samuel defined it just perfectly. The key phrase here is, without being explicitly programmed. The intelligence just sort of emerges from the data itself, not from some giant list of human-written instructions.
So what does learning actually mean for a computer? I mean, really? Well, it boils down to just three things. You've got a task, some experience, and its performance. Let's use our spam filter again. The task, T, is to flag spam. The experience, E, is watching you mark emails as junk. And the performance, P, well, that's just how much better it gets at catching spam tomorrow. If its performance improves after getting that experience, boom, it has officially learned something.
Okay, now that we've got the core concept down, it's time to pull out our map. You can think of the world of machine learning as having 3 major continents, and each one has its own unique landscape and its own way of approaching learning.
So, these big regions are supervised learning, unsupervised learning, and reinforcement learning. To make it easier, let's call them the teacher, the detective, and the adventurer. Now, for this quick expedition, we're just going to focus on exploring the 2 largest continents on our map, the teacher and the detective.
Okay, our first stop is the land of supervised learning, and just like the name suggests, this is basically learning with a teacher. It works like this. First, you give the algorithm a bunch of labeled data. You know, this email is spam, this one is not spam. Then, the algorithm studies all of those correct answers and starts to learn the patterns. And finally, after it's seen enough examples, it can look at a brand new email it's never seen before and make the right call all by itself. This is by far the most common type of machine learning you'll find out there.
But what if you don't have any labeled data? What if all you have is just a massive, messy pile of information and you want the machine to find something interesting inside? Well, that question takes us to our next region, unsupervised learning.
Right, so this is where the machine puts on its detective hat. It just sifts through all this unlabeled data looking for hidden structures and patterns. For example, it could cluster your blog visitors into different groups without you ever telling it what those groups should be. Or, and this is a big one, it can do anomaly detection. You know, flagging a credit card transaction that looks totally different from your normal spending habits. It is all about discovering these hidden patterns that a human being might just completely miss.
Okay, but just like any grand exploration, the journey into machine learning, it's not without its dangers. There are some serious pitfalls in the map that every single explorer needs to know about if they want to avoid getting lost.
And the first, and honestly the biggest danger, is just plain bad data. You've probably heard the phrase, garbage in, garbage out. Well, it's 1,000 times true here. If your data doesn't actually represent reality, any conclusions you draw from it are going to be flat out wrong. Welcome to the swamp of sampling bias. It's incredibly easy to get stuck in here.
Probably the most famous example of this comes from the 1936 US presidential election. There was a magazine that polled millions of people and then confidently predicted that Landon would win in a total landslide. But Roosevelt won. So what happened? Well, their sample was totally biased. Their polling lists came from phone directories and club memberships, which massively overrepresented wealthier voters. And on top of that, only a fraction of people even replied. So even though their sample was huge, it wasn't representative of the country at all. And that's a fundamental mistake we still see being made all the time, especially with things like online polls.
All right, so the second great danger isn't about bad data, it's about a bad model. And specifically, you have to watch out for something I call the mirage of overfitting. It looks really good from a distance, but trust me, it will absolutely lead you astray.
So overfitting is what happens when your model gets way too complex, and it starts to memorize the random noise in your training data instead of the actual underlying pattern. The best analogy is a student who just memorizes the exact answers to a practice test. They might get 100% on that test, but they'll completely fail when they see brand new questions on the real exam because they didn't actually learn the subject. Now, the opposite of that is underfitting, where your model is just too simple to even capture the basic pattern in the first place. Your goal is always to find that perfect sweet spot right in between.
So, with all these dangers, how do we navigate safely? Well, we need the right tools. We need an explorer's toolkit specifically for building models that are going to work out there in the real world.
And the single most important tool, the golden rule, is this. You have to split your data. One part is for training the model, and a completely separate part is held back just for testing it. And here's the key. You never, ever let the model see the test data while it's learning. This is the only way to get an honest, unbiased grade on how well it's going to perform on new information it has never, ever seen before.
A really common way to do this is what's called the 80-20 split. Pretty simple. You use 80% of your data to train the model, and you hold back that other 20% for the final exam, for the test. That test set, that is your measure of truth. It's what tells you how well your model will actually perform out in the wild.
And this brings us to a final, and I think really crucial thought. Machine learning it's incredibly powerful. But a model is only ever as good as the data it learns from. It has no common sense. It has no understanding of the world beyond the numbers we feed it. So as we build these amazing systems, we have to constantly be asking ourselves, what stories are we telling our machines with this data? And maybe even more importantly, what really important stories might our data be leaving out?